Hi, my name is Ashley Blackwell, and today I'll do my final presentation on the chest CT imaging CNN cancer classification project under Dr. John McKeeby for Data 675-9040. During this project, I built, trained, and evaluated a convolutional neural network for lung cancer classification. And this presentation highlights all that encompasses the early, middle, and late stages of the process. The scope of this project is centered on developing an interpretable deep learning model for lung cancer screening using CT images. The dataset contains around 1,000 de-identified images organized into 4 diagnostic categories: adenocarcinoma, squamous cell carcinoma, large cell carcinoma, and normal or benign tissue. My approach followed a clear workflow: data exploration and acquisition, pre-processing, model development, evaluation, and explainability, culminating in deployment. The project's goal was to demonstrate how deep learning models can support clinicians by identifying early cancer indicators while maintaining transparency through visual explanations. Lung cancer remains the leading cause of cancer-related deaths globally, and early, accurate screening is essential for improving survival rates. However, manual interpretation requires significant expertise that varies among radiologists. False positives can cause unnecessary distress, while false negatives can delay life-saving treatment. My project has explored how a convolutional neural network can classify CT scans into either specific lung cancer subtypes or as normal tissue, which will provide decision support in screening and diagnosis. Alongside accuracy, I also considered ethics, privacy, and security, recognizing that medical AI systems must protect patient data and assist clinicians responsibly, never replacing their expertise. The guiding research question for this project is, can CNNs be trained to accurately classify CT images into lung cancer subtypes or normal tissue to support radiologic screening? This question addresses both a technical and clinical gap, reducing human variability and interpretation while maintaining medical reliability. The goal is not to automate diagnosis, but to enhance decision support. Through tools like GradCam, we can visualize where the model focuses its attention and ensure that predictions remain clinically explainable and trustworthy. Ultimately, the problem being solved is one of consistency and transparency in AI-assisted image interpretation. The dataset was obtained from Kaggle's chest CT scan images repository created by Mohammed Haini in 2020, and it includes 4 labeled classes: adenocarcinoma, squamous cell carcinoma, large cell carcinoma, and normal or benign tissue. Each image was resized to 224 by 224 pixels and normalized to a 0 to 1 range for stable model training. The dataset was pre-split into training, validation, and testing sets, ensuring fair, supervised learning. During the EDA, I found significant image resolution variability and class imbalance, especially for large cell carcinoma, which had roughly 160 or 16% fewer samples. To correct this, I applied data augmentation and class weighting via ImageNet, ensuring equal contribution from all classes during model training. My exploratory data analysis revealed key challenges that informed pre-processing choices. First, image variability. The differences between brightness and resolution required standardization to 224 by 224 pixels. Second was class imbalance, and it showed that large cell carcinoma was underrepresented, and this reinforced the need for class weighting. Third was pixel intensity values ranged from 0 to 255. I normalized them between 0 and 1 to stabilize gradient updates during the model training. Finally, data quality. Some images were low res or corrupted, and this was improved by filtering and removing outliers. These steps collectively established a clean, balanced dataset ready for modeling. These visualizations illustrate the dataset characteristics. The histogram on the left highlights class imbalance, where adenocarcinoma and normal images dominate while large cell carcinoma has fewer samples. And the box plot on the right shows how image resolution varied widely, confirming the need to standardize all inputs to the same size. These findings directly influence my pre-processing strategy and justify the use of weighted loss functions during model training. In this project, I evaluated 3 distinct modeling strategies to determine the most accurate and generalizable approach for CT scan image classification. The first model, a baseline CNN built from scratch, served as a benchmark. It achieved about 30.6% accuracy, showing that limited data and imbalanced classes make it difficult for a shallow CNN to learn meaningful patterns. The model's class collapse motivated the move to transfer learning. Next, the EfficientNet V0 transfer learning model, pre-trained on ImageNet, achieved 85.7% test accuracy and a macro F1 of 0.855 and AUC of 0.969, clearly outperformed the CNN baseline model. EfficientNet's structure allowed the model to retain general image recognition features while fine-tuning for CT-specific characteristics. Early stopping, warm-up training, and class weighting contributed to stable, reproducible performance across all validation folds. This model happened to end up being the one selected as the final model for evaluation. Finally, the auto machine learning model used AutoKeras and AutoKeras' search feature to run 6 trials with an accuracy of 49% and a macro F1 of 0.48. This was useful baseline because it achieved higher metrics than the baseline CNN, but it did not outperform the transfer learning model. This slide summarizes the overall model performance and insights. Again, the baseline CNN trained from scratch reached about 30.6% accuracy and a macro F1 score of 0.11, confirming its inability to generalize beyond the training data. The AutoKeras model, or auto machine learning model, improved slightly to 49% accuracy, providing a useful automated baseline, but still showing instability and lower sensitivity across cancer subtypes. The EfficientNet V0 transfer learning model achieved the highest metrics: 83.3% validation accuracy, 85.7% test accuracy, and an AUC of 0.969. This demonstrated strong generalization and clinical variability. While examining the confusion matrix, most errors occurred between adenocarcinoma and large cell carcinoma, which aligns with the clinical overlap observed even among expert radiologists. These results validate that transfer learning approach not only provides superior accuracy, but also consistent, interpretable behavior suitable for future diagnostic support applications. The findings demonstrate that transfer learning, specifically EfficientNet V0 with ImageNet weights, produced the most accurate and stable results across all tested models. The model achieved 85.7% test accuracy, an F1 score of 0.855, and an AUC of 0.969. From an explainability perspective, GradCam overlays showed clear attention on the most important regions of the lung, confirming clinical relevance and trust. Regarding interpretability, these visualizations help clinicians understand why the model made its decisions, improving transparency. Consistent color schemes and self-contained charts supported accessibility in reporting results. And overall, the combination of accurate modeling and interpretable outputs demonstrates how explainable AI can responsibly enhance medical imaging workflows. Ethical practice considerations were central to every stage of the project. The dataset used was completely public and de-identified, meaning no personally identified information or PHI or demographics were collected or exposed. The focus was purely on developing a robust classification method for research and educational purposes. It's important to clarify that this model is designed solely as a decision support tool, not as a diagnostic replacement. No AI system should override the judgment of a trained radiologist or medical professional. Transparency and accountability were ensured through detailed documentation of every notebook, experiment, and metric. And this documentation not only supports the reproducibility, but also strengthens explainability and interpretability. And this shows how and why the model arrived at its outputs. In future clinical environments, additional safeguards such as HIPAA compliance, encryption, access control, and audit trails would be essential to maintain patient privacy. Ultimately, responsible AI development in healthcare depends on 3 pillars: data protection, model transparency, and human oversight. These principles guided my decisions throughout the build and deployment process. This project reinforced several key lessons about both the data science process and responsible AI practice. First, proper data acquisition and scoping set the tone for success. Starting with a clear understanding of dataset composition, quality, and limitations helped to avoid downstream issues during the modeling phase. Second, I learned the decisive role of transfer learning in limited data environments. EfficientNet B0's pre-trained architecture provides stability and accuracy far beyond what it could be achieved from scratch. This experience underscored the importance of leveraging prior knowledge from large-scale image datasets. Third, maintaining reproducibility and documentation was essential. Every step from pre-processing to hyperparameter tuning was logged, version controlled, ensuring that the project could be replicated and validated by others. And most importantly, this experience deepened my understanding of how data ethics, technical design, and system deployment must work together to produce reliable, transparent AI tools that serve human goals responsibly. And here are the primary sources referenced throughout the project. For Haney, 2020, this is for the CT scan dataset. Tan and Lee, 2019, this is for the EfficientNet architecture. Shen et al. In 2017 for background on deep learning and medical image analysis. Duke et al. In 2015 for vision design principles. And finally, Topal 2019 for perspective on ethical high-performance medicine. And each reference informed different parts of this pipeline, from technical implementation to visual design and responsible AI integration. Thank you so much for listening.